Welcome back, everyone. This is just going to be a short video. We're going to just look at the electron and the proton for a moment, because they're the things that pop up the most in electric fields. We're not sort of going by any dot point in the study design, it's just for your own information about protons and electrons, okay? So, electrons, let's first talk about that. So it was discovered by this guy. His name is J.J. Thomson. He won a Nobel Prize in 1906 for his contributions to physics. So he discovered the particle properties of the electron. He was the first one who sort of really pinned down the fact that an electron is a thing, okay, and it can be considered a particle. Funnily enough, though, his son, about 20-30 years later, actually discovered the wave-like properties of electrons. So this guy, he said, yeah, electrons are particles. They exhibit particle-like properties. And then his son comes along and says, no, electrons are waves. And that's what you're doing in Unit 4 when we deal with quantum physics. So that's just a funny coincidence. But the electron is the fundamental negatively charged particle, okay? It has a charge of, and this is the value that you're going to be using in this topic. It's got a charge of negative 1.6 times 10 to the power of negative 19 coulombs. Okay, it's a very tiny charge, a very, very small number. Okay, so 1 coulomb of charge is actually massive. Okay, you don't typically see charges on the order of units, ones, okay? They're very, very small most of the time, just due to the fact that the charge on a single electron is very small, although objects can have, lots of electrons floating around on its surface, giving it, a non-negligible charge. We call it the elementary charge, okay, because electrons are a fundamental elementary particle. They can't be broken down into smaller things, okay, and because electrons are the sort of the driver for electricity and everything that sort of runs on electricity, we use its charge as the sort of basic unit of charge, okay? So we say that the electron has an elementary charge. It is, 1 unit of charge. And we usually give it the symbol little e, okay, for electron, or QE for charge of electron. Okay, Q generally represents a charge, just like M represents a mass when you put it in an equation. Okay, so how many electrons do you need to make 1 coulomb of charge? Well, you just divide 1 coulomb by the charge of an electron, and you get this massive number here, 6.25 times 10 to the power of 18. So you need that many electrons to make up 1 coulomb of charge. That's a massive number, okay? And so that's why you don't typically see things that have charges of 1 coulomb, okay? Very often they're like micro coulombs or nano coulombs or something like that, because you need heaps of electrons to make that charge quite a lot larger. All right. Now, the charge of the electron was not known at the time of its discovery. Okay, people knew it was charged, but they didn't know what its charge was. That came along a bit later, during an experiment by Robert Millikan, and he's the one who sort of started pinning down what the actual value of the charge was by a very ingenious method of measuring the charges of oil drops. You can read about it yourself. Just Google Millikan electron charge or something like that. But we've now, well, not me, but, scientists in general have defined the charge of an electron to be exactly this number here. Exactly that. Okay? Previously, they based a whole bunch of SI units off, how can I put it, sort of, well, let's take the kilogram, for example. They used to have this metallic block sort of stored in this underground chamber, and that was defined to be the kilogram, okay? But you know, things that are made of atoms, the atoms can rub off and stuff like that. And so over time, the actual kilogram block that was used to define the kilogram would have lost some mass. And so the actual value of a kilogram would have changed over time. So there was this whole push in recent times to sort of make SI units based off things that don't change over time. Okay, and one of the things that they've done is they've just said, yep, the charge is exactly this. Okay, so they're not basing the charge off some magical object that exists in some underground chamber somewhere. They're just saying, yep, that is the value of the fundamental charge, the elementary charge, and that's that. Just like they've defined the speed of light to be exactly, 299 something 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 something. It's not based off anything. They just said, yep, that's what it is, and that's it. Okay, so that's an electron, negatively charged, discovered by this guy. It has this value here, and we call it the fundamental or elementary charge, and it has a symbol E or QE. Cool. All right. Protons. Protons were discovered by Ernest Rutherford. He did this experiment where he fired things at a very thin sheet of gold or something like that, and he found that sometimes these particles that he were firing at the sheet sort of bounced right back. Okay, so he sort of realized that there's this very small concentration of something very positively charged at the center of an atom that was making these things return back to where they came from, and that was basically the discovery of a proton. Okay, so he won a Nobel Prize, but not for physics. He won it in chemistry for something unrelated. Bloody chemists. And yeah, so that's how a proton got discovered, basically by this guy. So protons and electrons, I mean, they're the things that you're going to be working with when we deal with fields. Atoms in general have the same amount of protons and electrons. If they don't, then you call it an ion. We know now that a hydrogen atom has 0 net charge. Okay, that means it's got a single proton and a single electron. And we know that the charge is neutral overall for that hydrogen atom, so it must be that this proton has a positive charge. Okay, the positive charge matches exactly the negative charge of an electron, otherwise they wouldn't balance out properly. So a proton has a positive charge equal to this number. Okay, it's the same thing, just not negative. All right. So you can describe the charge of a proton with the symbol E, just like you would describe the charge of an electron with, say, negative E or something like that. All right, now when we're dealing with protons and electrons, you've just got to keep in the back of your mind that a proton is about 1,000 times more massive than an electron. Okay, it has 1,000 times more mass. Okay, so the mass of a proton is something like blah 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 times 10 to the power of negative 27. The electron is 9.1 times 10 to the negative 31. So it's 1,000 times more. But the charges are the same. Okay, so don't worry about the fact that protons and electrons are different size particles. It's the charge that matters when we talk about electric fields. Okay, so that's just an aside. We're just talking about protons and electrons. If you've never sort of encountered them before, if you didn't do unit 1 and 2 physics, that's what protons and electrons are. Okay, their charge, very important number. That's what you're going to be using. 1.6 times 10 to the negative 19. And you might like to use the symbol E to represent the charge of a proton or an electron. And just remember, protons are positive, electrons are negative. Cool. All right, that's it for that video. I'll see you next time.